Awesome. Now that we know what partial derivatives are, we can use them with respect to regression or other machine learning problems in order to identify how to adjust our model parameters in the direction of lower cost. Recalling our four-step machine learning process from earlier in these live lessons, remember that we first calculate m times x plus b for our line regression model, and then we pass the predicted y into our cost calculation, and we compare that y hat with the correct y. So our estimate of y is compared with the correct y using our cost function. And then in the third step, we previously were using automatic differentiation, which was applying the chain rule to allow us to go backwards from c through our cost function all the way through the forward pass back to m and b in order to get the slope of c with respect to m and b. In the fourth step, we then used those slopes that we obtained through automatic differentiation in PyTorch in order to allow a gradient descent optimization to know whether to move m and b slightly up or down in order to reduce cost. And then that way, the next time we do our forward pass, our y hat should be slightly closer to the true y. Previously, we had to use automatic differentiation because although we knew what differentiation was, we couldn't calculate the derivatives of cost with respect to our parameters m and b because we hadn't yet learned partial derivative calculus, which is necessary for us to calculate cost with respect to multiple parameters in our model. So now, with an understanding of partial derivatives under our belt, we're going to return to the same machine learning problem fitting a line to those 8 data points, but now we're going to, by hand, use partial derivatives to calculate the derivatives of cost with respect to our model parameters, and this will allow gradient descent to proceed on a slope between cost and our model parameters m and b that we now understand. So we'll have a better understanding of what these slopes are, and that way our model will be able to descend the gradient of cost and find the point in the cost curve with the lowest possible cost. So we'll find this valley of cost here where the slope is 0. So in these diagrams here, we just have one parameter, a single parameter. Now recall that even our very simple regression model of a line has 2 parameters, m and b, but just for the moment, pretending that we have a single parameter so that we can visualize this in a 2-dimensional space, we start with a randomly initialized parameter value, and then we use the slope of cost with respect to any given model parameter, so it could be m or it could be b in our case. And so we determine the slope of cost with respect to that parameter at a randomly initialized point, and then knowing that slope, we can use gradient descent to take a step. We can adjust this parameter p leftward, so to a lower value, and at that point, our cost will be lower. And we'll repeat this process multiple times, and each time we'll be at a new point on the cost curve, and we'll continue to make adjustments to p until we gradually make our way to the lowest possible cost. Most specifically, at this point here, the gradient of cost with respect to this model parameter p will be equal to 0. The slope is equal to 0. It's flat. Let's jump to a hands-on code demo called Single-Point Regression Gradient. So this is going to be a new notebook. And in this notebook, we're going to deal with single points at a time, which will make calculating the gradient of cost with respect to our model parameters a little bit easier than if we use multiple data points. But we'll come to those multiple data points later on as well. Okay, back in our ML Foundations GitHub repository at github.com/johncrone/ML Foundations, we can now pop into the Single-Point Regression Gradient Notebook. As always, you're welcome to view statically in GitHub, but I recommend that you follow along dynamically in Colab. As usual, we'll go to Edit and clear all outputs, and now we are ready to rock. So in this notebook, we're going to calculate the gradients of quadratic cost, a particular type of cost function, which I'll go over in a moment in the code. So we're going to calculate the gradient of quadratic cost with respect to a straight line regression model's parameters. So this is the same simple straight line regression model that we've been working with already in these live lessons. We're going to keep the partial derivatives as simple as possible by limiting the model to handling a single data point. So that is the key difference here. We're working with single data points, and for the first time we're going to be working with quadratic cost, which is only applicable to single data points. All right, so let's import the PyTorch library. And then we'll use the same data as we did earlier in the regression in PyTorch notebook, as well as the same data that we used for the Moore-Penrose pseudo-inverse back in my algebra live lessons, if you were following along with those. So we've got the same vector of x's and the same vector of y's. Note here that I'm giving it a different name. Previously, I just called it x or y, but here I'm calling it x's and y's plural because we are going to be grabbing single individual values from each of these vectors and calling those x and y variables. Just as in the regression in PyTorch notebook, the slope of a line is given by y equals mx plus b, so we have the same regression function here of mx plus b. Also, just as in the regression in PyTorch notebook, we are going to initialize m and b with random near zero values, and I'm going to use the same ones, 0.9 and 0.1 respectively, for m and b, but you're welcome to use other starting values, ideally near zero values, at your end. Again, to keep the partial derivatives as simple as possible, let's move forward with a single instance I from the 8 possible data points. So I'm pretty arbitrarily going to grab I equals 7. Because Python is 0 indexed, this is the 8th and final element of the vectors x's and y's. So let's have a look at those values. X is equal to 7, y is equal to negative 1.37. So as you can see, those are the final elements in our x's and y's vectors. Now that we have our data points and we have our model and we have our model parameters all set up, we can start going through our 4 steps of the machine learning process. The first step is the forward pass. We can flow our scalar tensor x through our regression model to produce a single y-hat estimate, a single estimate of the correct value y. So we have our correct target with an x of 7 is negative 1.37, but prior to any model training, this y-hat is not going to be close to the correct y. So let's have a look at what it is. We pass it through our regression model, which performs m times x plus b, and with our randomly initialized m and b values, our y-hat estimate comes out to 6.4, which is nowhere near negative 1.37. In step 2, we quantify how nowhere near y-hat is to the true y, and so in the regression in PyTorch notebook, we use mean squared error, which averages quadratic cost over multiple data points. However, with a single data point, as we have here in this notebook, we can use quadratic cost alone. So quadratic cost is simply defined by taking y-hat minus y, so the difference between our estimated y, in this case it's going to be negative 1.37, and our true y, which is 6.4, and then squaring that difference. Remember, I described earlier with respect to mean square error cost that we do this for 2 reasons. We do this because that way cost is always positive, and it also means that large differences between y-hat and y correspond to an exponentially larger cost. So we're less tolerant of big differences between y-hat and y because bigger differences produce an exponentially bigger cost. All right, so let's define this quadratic cost function. Quadratic cost can also be called square error. Those are synonyms. So very simply, in my squared error Python function here, we're performing y hat minus y squared, just what we have here. Once we have that function, we can pass in our y hat and y values. So negative 1.37 and 6.4 go into our squared error function, and we discover that our cost for that single data point is 60.4. Now, up to this point, we've always relied on automatic differentiation in PyTorch to calculate the gradient of cost with respect to our model parameters m and b. And we did that by using the backward method on our cost variable. Then we can go look at the partial derivative of c with respect to any parameter of our choice, any variables that we set gradient tracking on, which in our case are the two parameters in our model, m and b. So now using the partial derivative notation that we know, we can say that this value here, 108.8, this is the partial derivative of c with respect to m. It's del c del m. And then the partial derivative of c with respect to b, or del c del b, is 15.5. So we've yet again used the PyTorch auto diff functionality to get these partial derivatives of cost with respect to model parameters, but we now have enough theory that we can go and derive for ourselves by hand what del c del m and del c should be. So we'll do that in the very next topic. Pretty cool, right? We'll jump to the slides now and take a crack at it.